Hello, welcome to, what is this, episode 7, I believe, of me working on this. Well, I'm not sure, I'm not sure how many this is going to take, or how many I'm going to get in today, but hopefully I keep it down to one episode's length worth of work, and don't have to chop it up again, like I did on the last 3 videos. Anyway, more importantly, where did I leave off? I had just built this set subtract thing. I still need to build a set intersect, but before I go that way, I want to also, I'll put in a thing here to remind me that I need to actually finish that, but I want to redo these things that are not working. Hold on, I want to close my window so that I don't get beeping. It's been not that loud for a little while, so I didn't think that was going to happen. But anyway, moving on. I want to get the rest of this stuff, like building and working again, or at least not working. It was never really working, at least not in the sense of it had been tested. But I want to get it at least back to the point where it's there it is. All structured the right way again. So some things have changed. This transition, the condition thing now is one of these case things, right? So and then that has a condition set, which is itself a series of condition nodes. So what I essentially want to do is say that I'm constructing a condition. I'll give it the context. I'll give it the characters, and I'll give it the flag check and flag check value. And that should be enough, I think, for me to be able to define the first 2 here. Oh. Right, so that constructs the condition completely. That moves the responsibility of this into here. And this stuff isn't really even done anyway. This one is just, yeah, we just need one of these. I'll probably do it like this. Well, yeah, I'll do it like this. Alright, so it's going to take a little more to construct these things than it did originally. Okay. Right, so what's changed here is this case used to just be a thing that was like an enum on several different, like it was character array, end of file, where is that? It's right here. Character array, end of file, and fallback, right? And these are still the way we're specifying things when we define them, but we're converting them when we like build the model to not actually store these, but instead to store this more generic condition set thing that'll let me do some of the optimization work I want to do. And so I have to translate the meaning that this communicates into the more generally, like the thing that this represents, or the way, into a piece of data that represents the original meaning in this format. That's what I should say. Alright? So, for instance, this here is taking an array of characters and a flag check. Potentially this will be null, in which case there is no flag check, and if it's not null, then that's the only flag check that case has. So how do we construct one of those? Well, first of all, it's this type, so let's just take that. I'll call this like the transition case, or just result will be fine. Set its kind to, this is a condition set. And now the more interesting part is constructing the condition set. So the construction of a condition set, I think we'll want to make just it's hard to say. So I guess what I probably want to do is do it all out by hand each time. I'm not sure. Anyway, either way, the point is I'm going to need one node. So let me allocate one of those. Right? So we take the node, we save it on the list. Alright, now we need to fill that node up with everything besides its next pointer so that it is correct, and then we're good. So its inputs we can get by doing on the arena one input for every character in there. And then we need a quick loop over those. I believe that's called size actually. And then yeah, just convert that to a U16. There we go. So there's our inputs. We do need to store the input count as well. That's just characters.size. I'll need to cast that most likely. Just fine. And then there's the flag pins. So for the flag pins part, what we do is we look at whether or not we even have a flag to begin with. If we do have a flag, then we're going to allocate one of these flag pin nodes. Come on, there we go. And push that onto the condition set, flag pins first, last, first, last pin. Right, and then I just need to fill a pin in with this and this. Okay. It's really hard. My brain will keep on looking at this code and thinking wow, is a linked list really the right thing to do here? What about an array of bits, an array of booleans maybe would be better for the flag pin, or no, you need at least two states because there's the unpinned state. You need at least three states because there's the unpinned state, the pinned state, and the pinned positive and the pinned negative state, right? And so on and so on. My brain's doing all this, thinking through other ways this could be organized. And then I realized that all of that would only achieve an optimization of this code instead of actually doing anything useful. I mean, it might be a little bit easier to do something like setting a pin. There might be a few less lines of code right here. But the amount of work it would take to figure out how many to allocate, how to pass that allocation count around through the whole system so that everywhere that you need to do manipulations on flag sets, you know this correct you know the correct size to allocate for that and all that kind of stuff is just like what is it's a lot of work. It's it would make this take longer to write if I did do that. And so it's a little hard to get my brain to stop thinking those things through. Like I really do want to optimize the code when I'm writing it, but I have to remind myself that this code, its primary concern is that it get working first of all, and that it be easy for me to keep it working. And linked lists just are usually easier because they're like flexible. They have wiggle room. You can allocate them on the fly, like you can grow them one at a time without overthinking anything. You can recombine things and concatenate things, and they get the best like semantical characteristics, even though they feel so weird. And so doing things this way, the point of it is that it gets me the flexibility I need to write these things that are somewhat intricate without having to overthink it, except that I still do overthink it sometimes, and it wastes a lot of time, and I end up like thinking through details that I then realize are only optimization details, which I don't really need for there's no huge need to optimize my generator's runtime unless I start generating really big things with it that are taking too long, So why is that a problem? Flag pins, condition set. Oh, so you actually are the wrong thing. It's not condition set flag pins first and last. It's the nodes flag pins first and last. Whoops. Gotta get back into the habit of hitting F6 for this project, not F1. Okay, what's going wrong here? Oh, those say next when they're meant to say node. Okay, so there's our constructor for the character array. Let's make another one for the end of file. This one just always does 1 as its value right here. And that one thing is SMI EOF. That's the only thing, right? So code duplication between here and here. What do I want to do about that? Probably this. I think this will be the easiest way. So I won't initialize it. I will just allocate the inputs. And then the little piece of code that is different is this happens when we are constructing one of these. Result.kind node. Yeah, I guess I have to do. I mean, I want a multiple return here, but that's going to be a pain in the butt. It's going to create extra code to define another type. There's a way to get the right behavior without having to go down that road, I guess, is the most important detail, but reason why I'm not going to do that. Alright, so the difference between the normal construct and the EOF construct is simply that right there. Right, that's the difference. Okay, so that's nice. Wrong one. Come on, Give me, there we go. What are you complaining about? Right. What are you complaining about? So the thing you got is a... Right, we need one of those. There we go. Now why are you failing? Construct UF. I thought we had that right up here. Did I lose the name? There we go. Okay, so we're not quite done because this is not done. The thing that does fallback isn't done. So what I need to do to make a fallback is I need essentially I need all of the possible inputs, so 0 through 256 inclusive, in an array with the only pinned flag being this one potentially to start with. Right, I need that set. Then what I need to do, you know what I should have done? That would have made a little bit more sense. Is for this code here, just can make the condition directly. Hold on, I feel like I'm going to sneeze, but it's like it's not coming there. It's not going that far, you know. But if I just did conditions here, then this would actually be correct, the way it's set up. And then this, because those already have the kind anyway, and that's pretty easy to do it that way. And then this can just be the condition set. Yeah. Right, so that's cool, and then all that has to change is these are a little bit off. Right. I feel like that's good. Then what I need is I need a condition set that can catch anything. And I think that's all I have to do for now. I think that's the best way to do it. I mean, the other option is that I could, when I construct a fallback at that time, go through and check how it gets eclipsed by the previous things, but I don't really see the point in doing that. We have a thing that simplifies transitions already, and it could do that. Or we also have a thing that like when we actually go to inspect the transitions to optimize out these peaks, which is what we're trying to get around to finishing, that's also going to have to do eclipsing work that builds up over time. So either way, all the information I need is going to be available. So I think the easiest thing to do is to just say, look, the condition set when it's a fallback is just one that looks like this. Right? Do that. Do that. Give me 257 slots. Might as well do that, right? So there, that just gives me one of every possible input, and then if there's a flag check, it gets passed down as well. And then there we go. That's the actual constructor stuff done. Let's see what's gone wrong. What's gone wrong? condition set. Okay, so now the eclipse thing is all wrong because first of all, I don't need to do it on the whole case thing. I need to do it on the condition set. But more than that, a condition set eclipse is really just going to be the same thing all overall as the subtraction anyway, right? Wait, did I never do the flag subtraction part? I didn't. Yikers. So, last time I was working on this, I was kind of fading a little bit by the end. Like, I was not... didn't quite have the energy to fully think through one particular thing, which since then I've stopped myself and asked if I actually want to do it exactly the way I'm doing it, and I will see if I can explain myself. Okay, good. This is still here. So the way we're doing flags, I think, is going to be necessary. It's possible that I could just do the full flag set, like the actual list of all possible values, but that's just so... Like, if my problem with this is that it's slow, then that's so much slower. That would be simpler. And maybe that's a good enough reason to do it that way, but I don't think that I can really do that. I think that would be too much of a performance, like, absurdity, right? So I had a different idea, which is right now what I have is I have these things that are called condition node, and then type information that a node, like the type structure of a node is that it has some like input set and then it has some flag set, and they're like, it's a pair. Each node is a pair of the set of possible inputs and the set of possible flags, and that node represents the set that you get when you do this, essentially. The set of all pairs that include valid inputs and valid flags only, right? Any combination of valid input and flag is allowed. But then it's often the case that I need to construct sets that have like this happening, right? Where there's like, it used to be possible to just say 1 through 5, A through H, it's all valid. But then you wanted to take out a chunk that doesn't take out all of a particular set of numbers. So 4 and 5 didn't get, or sorry, A, B, C, and D didn't get completely removed. There's still some A, B, C, and D. There's also still some 1, 2, and 3. So you took out some 1, 2, and 3. You took out some A, B, C, D, but you didn't take out all of any category of thing, right? And so you have to like punch this hole in the system, and how do I handle that? And well, we did this last time. I have like a split it, and so I have a node here and a node here, and I chain them together to make a union of those sets. But the problem is, with all that, that then what I'm talking about as a set is a node, basically an array of nodes, right? Something like that, right? So my node is defined as the cross of these two things, but my set is like a list of these nodes that when union together gives me the full set that I want. The problem with that is it's very hard, like it's binding things in the wrong order. If I was a little bit more careful with how I said that this was going to work, I think there'd be another way to do it, which is that I may want to say that a node is actually made up of an input, and this is like a flag pin set, right? This is a flag set based on pins. What I could say is I still want a flag set, but what I want to do is I want my flag set to get redefined. So maybe the best way to do this is to say, let's define what a flag set was defined as. So a flag set was defined as a like list of pins, right? So it's like n of these things, right? Or to be more exact, the flag set was the intersection of all of the flags that agree with every pin. or the intersection of each set that each individual pin represents, where each pin represents a way of cutting the set of possible flags in half. So if I pin a flag to 1, then I'm saying half the flags are invalid. All the flags where this, all the flag set, all the fields where this particular flag was a 0 become invalid when I pin it to 1. So that cuts the set space in half, right? The set of possible bit patterns gets cut in half, and then I intersect a bunch of those together to construct the particular set of flags that I am interested in. And we don't have any problem with the fact, like, yes, that means we would have a big problem if we needed to poke in one particular flag, but that's never the way flags are structured. I think I kind of determined that I was happy with using flag sets that way, within the limitations of what that allows me to represent. But it means that if I want to do an operation on a flag set that turns it into a chain of flag sets, so there are some operations, flag set minus flag set, that want to map to like a flag set array. And the problem with this now is if I had a node and I wanted to take this the flag set and this node and subtract it, I could get a flag set array, and then I can't represent that as a node. And so hierarchically things get confusing because I have a node, it contains an input and a flag set. I'd kind of like to be able to just say, hey, this node and that node are doing an operation with each other, and this node says, take my flag set and subtract that other guy's flag set and give me the result. Well, the result isn't actually representable without building a full set. You have to like skip over the node, and so there's this whole nasty thing going on there. I think what I need to do is rebuild the hierarchy and say that what actually happens is that this has one of these, right? And so a flag set actually becomes like a flag bisection, or no, a flag like pin set or something like that. And an actual flag set would become the array of flag pin sets, right? And then this can just contain a flag set again. So the reason this is cool is now my operations for flag sets will be possible to define. Yes, I'll have to deal with the fact that like it means that I'm doing operations on unions of these things with unions of other things. So like a flag set minus a flag set now has to be expanded in the following way. It is actually this intersection minus this intersection, right? And then I have to figure out how to do all that stuff. Sure, that's going to be weird and different. I mean, it's actually not that different from what we already worked out up here. This is basically the same logic. The difference now is just that I'm saying a node can have within a chain of unions together flag sets, or flag pin sets, right? This naming is confusing. But I feel like that's gonna be better. So I kind of want to like just take another step back here and do a pass over the organization of all this. So I have this thing called a flag pin set. I don't really know what to call it. Maybe it's a flag pin lists or something. A flag set would just be a series of these things so that we can union them together. And then we need to keep track of how many of those things we have. And there's a flag set for realsies. And then one of these things here, I'm just going to call it like a node or a condition node or something like that, to shorten these names down a little bit. And it's got a flag set, and it's got an input set. And so I need to define the input set as well. Right? So there we go, and then we can get rid of that, and then a condition set is just going to have to be a chain of these things union together as well. So in this way, we can represent any particular set we have to, and the most likely sets are the most compressed, I think. And we avoid ever having to fully list out all of the flags and do operations directly on them. We still have to list out all the inputs because there's not really any reducing them to a smaller data structure, I don't think. And so then this can just be called the condition set directly. Condition kind is a weird name. Case kind is a dumb name. Transition case kind. What do I even want to call that? I'm not sure. So yeah, let's get rid of you. Transition case kind is fine for this whole thing as long as I build condition set in there like that. So legal, these are just like intermediate actually stored in transition case kind field, right? And now what I have to do is all the code that I wrote before is still basically correct. It's just not organized correctly. And I think that this is going to simplify certain things. I hope. Okay, so then what we need is for every one of these things, we need to define how we do a couple of operations. We need to know how to copy one, so we need to know how to copy a flag set, we need to know how to subtract two flag sets. We need to know how to intersect two flag sets. And I think we probably need to know how to union two flag sets. We need to do all the same things for input sets. Oh, we probably also want to know how to construct a flag set from a given flag check. Okay. And we also probably want to know how to construct an empty flag set. Or rather, a default flag set that is the opposite of empty. Alright, so none of that is implemented yet, although a lot of it will be copy-pastable from other stuff, or not that complicated to get working. Same thing again with input set. I might as well just do this. Besides for the constructors, an input set looks like this. Intersect, union, subtract. We need to be able to copy them as well. Right, okay, so we can copy, subtract, intersect, and union. And then I need to be able to construct this from several different ways. I need to be able to from from a character set array. From a character array. Right, I need to be able to construct one from an end of file, and for an end of file, and I need to be able to construct a fallback. Right, those are like ways I build those things. Now, if I build all that, maybe the rest of this will not be as complicated. So first of all, let's just see. Yeah, I'm gonna just try to like power through these and see if we can get this actually to fit together the way I think it could. So we want a new copy of the set parameter. Okay, copying is pretty straightforward, right? We don't even need to think about the semantical meaning of this right now. Right, just some comments to help me remember the structure here. Okay, and all we need to do for nowsies is create a new flag pin list. From the existing list. What? No, 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 no. Do not tell me you just did that. Oh my god. That was pretty bad. That was kind of essentially a disaster, but let's take a look. If I manage to recover. Okay, so yeah, the word value still exists everywhere, so I didn't do that. I think I accidentally hit the key to replace in all buffers, and I don't think this version of 4coder had like universal undo, like a cross project undo, so it was a bad situation. Anyway, I need to remember the name of everything. We lost all that stuff in the scratch buffer because of that. Do we have flag set? Yeah, we still have flag set. Handler kind. Flag. That's not helpful though. Flag set. Okay, this is the wrong. Okay. So I'm going to have to name these differently. This is going to be called field from now on. Okay, so not quite a disaster anymore, but this is still really annoying. At least I caught the fact that flag set isn't a usable name. In fact, all of these just need to say field, where they used to say flag. Damn. Okay. So every occurrence of flag check flag is supposed to be flag check value. So I did save this file after the mistake. Okay. Where is that? I was just writing it earlier. No. Yes. Okay. Back to this. We create the new node. Now we just need to make sure that whenever we make one of these new lists, we are pushing it onto the results. And whenever we are creating one of these new pins, we are pushing it onto here. Right? Okay. 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 Right. That's what I was originally trying to get done. I was renaming this all to be flag and flag. Yikes. Good. Okay. Now if I go up here, let's get this field set implemented. Jeez, that was scary. So copy. It's looking at the set, so iterating the set. For each thing it sees in the set, it's creating a new list, it's putting it on the result. The result count got set up here, by the way, so we don't need to increment. It's setting the new list count equal to pin list count, and we're iterating the pin list. For each thing we see there, we create a new pin, and then we're done. Okay, so that's how we copy one of those. It's just a doubly nested, doubly linked list copy. Okay, how do we do a field set subtract on one of these? So what we have are our atomic things are these pins. So we have a pin, intersect pin type thing. And then we have a union of those. And then we are going to subtract that from another one of those. So what am I talking about? What is all this? Well, let's just bear with me here. Let's say that each pin is one of the following sets. A, B, C, D, E, F, G, H, I, J, K. C, D, E, F, G, H, I, J, K. Right, so 9 uppercase and 9 lowercase. So we're talking about A intersect B intersect C, D intersect E intersect F, G, what was I thinking? G, H, I, there we go. Right. So, how do we do that? How do we do that? See if I can remember some of the rules that will help here. For one thing, we can always distribute over unions, unions over intersections and intersections over unions, if that helps to simplify it all. But what about, let's start with, what is the subtraction of A union B minus A union B? Let's peel this from the top layer down. What set do you get when you do that? And when I say what set do you get, what I mean is how do you get a set that you represent without a subtraction sign in it? How do I rewrite this with no subtraction sign? Just using intersections and unions, like intersections of, or unions of intersections. So if I can rewrite this as unions of intersections, then I can represent it in the same format as the data itself can allow. So how do we get there? So A minus B, and I have one other thing I can rely on, which is I also have the ability to get a complement. So if I write complement of A equals like the all set minus A, right? So at any time I need to, I can do that. So the first step we can do is that this is the same as A union B intersect the complement of A union B, little a union little b, right? Okay. So that's one step closer. Now, I need to rewrite this because I can't get the complement of A union B. I can only get the complement of little a and little b separately. So, if you take A and B and union them together and then you complement, that's not the same thing as taking A complement union B complement. It's not the same thing. I think it's the same thing as intersecting them. Right? In order to be in this, you have to not be in A and not be in B. Okay. So now if I can pull off an intersect, we'll be done. So how do I do an intersect of this type? Well, you can distribute that over the union, right? A intersect all of this, union B intersect all of that again. And then that actually can just be rewritten like this. Right? So the point of this exercise is to see what pattern this will become when I try to break it down. I think this is correct. If something was in A, and if it was in one of these two things, then it'll either show up here or here. So if it was in A, but it was not in little a or little b, then it should show up. That's what we have. In big A, not in little a, not in little b. Included, yes. In big A, but not in this, and not in this. In big B, if it was in big B, it would be included on this side then, right? So this is good. I can mark it like this now. I'm going to shorten all things to un and int. Okay, so that's how I can subtract all of that from all of that. But I still haven't answered how I'm going to do big complicated stuff like this, because this doesn't have intersections within the big A and B. So now, if I replace here each of those with a different rule, right? So we'll forget A and B, we'll switch to C's and D's and E's and F's, right? So big A will be C int D, and big B will be E int F. And then we can do the same thing again for the lowercase versions, and then substitute. This then becomes C int D, C int D, E int F, E int F, C int D, E int F. Now the problem is these things are again not representable, so we need to figure out how to rewrite that part. So I'll just take one of them as an example and say what happens when I rewrite this to have the intersections all the way, like the complements pushed down to where I can actually apply them. It becomes this, right? It seems reasonable. In order to say that we C int D the same as saying all the elements that are in C and D. If I want all the elements that are not in both, then I want all of the elements that are not in C and all the elements that are not in D. Or to put it another way, you're included in this set if you are not in C or not in D. You're included in this set if you're not in both C and D. Those are actually the same thing, right? Yeah, all of De Morgan's rules should apply, I'm pretty sure. So, so if we just plug that replacement into this, we would get C union D. Keep that in parentheses for a minute so we don't forget. Union F. And so that can be applied here. Right? Now what I need to do is take whatever rearrangements it requires to have this become a union of intersections. Right now it's a union of intersection of unions. I can't have unions down here at the bottom. So how do I rearrange x int w x int y and z, right? How does that rearrangement happen so that it's union on top instead of on bottom? Well, I'll apply just to this part first. That's x int w unioned with x int x intersected with y union z, right? X intersect W, X intersect L, X union that and that together. Okay, and again, we can distribute this over these, which leads to and then there's some simplification I can do here because we're basically saying, well, that's the problem, is there's not. This is overcomplicated and this is the simplification, but I need it in this format because that's the data structure that I actually have. Right? I can't, for instance, go, oh look, I could just intersect this whole thing with YZ later. No, we we can't. We can't have intersections at that level. Although I think I did that wrong. Yeah, it feels like I did that wrong. I'm trying to intersect this phrase with both of these phrases. Right? Because that gets me with a union on top, but then I still have a union at the bottom that I just put there. Maybe I want to go the other way around. Maybe I want to take this phrase and intersect it with each of these. Oops. So now what I have is a union of intersections of unions, but I can take this. Geez, this is too deep. I might need to do an extra layer to make it work out reasonably. An extra layer of the type structure. Because this would work out like this. Right. And then finally I can rewrite that as a union of intersections like this. So, what did I learn? I learned that if you do that, the way it expands is this. You have to basically, I see, we're taking chains of the intersection. So x, w, y needs to be in the part of the union, x, x, y, XWZ and XXZ, right? Each one of those needs to be unioned together. And that makes perfect sense. So yeah, I think that's just what I'm going to have to do. I'm going to have to get that whole thing up and running. So let me just take a case now that we can actually work out. I mean, I have that big one up there, but that's going to be too many letters to do the text for. I want to simplify it. So let's do that and that. And then we're going to do C and D. how do you compute this? Well, you do something union something minus something union something minus something union something is determined by this formula here. So let me drop that in. Now the first thing in the first union is that. The second thing in the first union is that. The first thing in the second union is that. And the second thing in, oops, and that. And the second thing in the second union is that and that. Okay. Then, if I want to rearrange this so that, right, we just push those those complements down a layer. This becomes that union that union that, and if we take both of those, that is the same on both sides. Okay. So we started off with A intersect B union C intersect D. A intersect B union C intersect D, right? Then we said, okay, rewrite this once by using the subtract rule for A union B minus C union D, right? And we got this. Then we push those things down here. Now the only thing we have left to do to make this work is we need to rearrange that there are no unions underneath intersections in the expression, right? We want this to be strictly unions and then intersections underneath them. And that part was what we worked out right here. If we have something intersected with a union and another union, you have to do this sort of almost like FOIL type thing. First, outside, inside, last. Yeah, it's exactly like FOIL. You're doing, pick one from each group, combine it with that. Got it. So this becomes, this thing is pick one from each group to add into the intersection. So A, C. There we go. There's our first one. Union that with A, D. Union that with D. Sorry. B, C, and then union that with B, D. Right? C, D. I'm starting to see something here. So it's not clear to me that this is actually gonna be a good idea anymore, because now that I see how the formula works out, yeah, that is essentially doable, but there's this like n times m times blah blah blah. Like if it really does get arbitrarily complicated, these expansions. So like all it took to make this thing become this big, there's now a set with 1, 2, 3, 4, 5, 6, 7, 8 lists in it, and each of those 8 lists has 4 elements in it. And how did I get to there? I got to there from having a subtraction with 2 and 2 on each, became 8 and 4 on each, and if that got subtracted by something else, it would immediately like grow like that again, like just expand out from, if something that was just this big again minus this thing happened, it could grow out to be something like 16 big, I think, maybe more, as we just start getting huge. Like this is 1, 2, 3, 4, right? So if you imagine all of this will become 4 possibilities of this, and all of this, so this would become 4 times 8, which would be, yeah, it'd be 32, right? So it would create 32 combinations, and then you have to multiply that by, it would be 64. It'd be 64 to do this again, like to take this and subtract this again. And so the point is it actually explodes out exponentially, and I think that makes it slower than if I was just keeping lists of these things and looping over them linearly to remove stuff, right? I'm starting to think that that would actually just be better. And then I could just say that we're going to arbitrarily like limit ourselves to 32 flags. Because then it's not that hard to like, well, actually I wouldn't even need to do that. We can say that the limit's higher than that, but point is, no, we would actually have to say the limit's lower than that. At 32 flags, we would end up with millions, billions of things in most sets, right? So that is the reason this works, is that if I want to have more than like 10 flags, yeah, it's hard to say. It's hard to say. This does blow up fast. I mean, some of it will simplify down, so a lot of these will end up becoming empty sets and maybe disappear. But I think I have to do this, yeah, because yeah, the problem is that compression problem. Yeah. So if I go ahead with this, because now I see the pattern, we're going to have to, using the complements of all these things, thread through each, not like multi-threaded, but like construct all the combinations that let us sort of grab one from each option on this side, which becomes n times m blowout, so 4, and then times the number of things in this union. These don't get actually altered, but we have them in like one spot for every combo. But the cool part about that is that means we can actually do this in 2 stages. We can break the computation for this, can get broken down into the computation of this and the computation of this, right? So then we can do it as, we don't need to do the iteration across the whole list at the same level as everything else. So I think this is what I need to do. We're going to take the list minus b, the whole set. And that should return to me a full-fledged set. So this would be a partial. And then all I have to do is combine that with the result that I have so far. Okay, so now we need to ask ourselves, what's the best way to implement just this part right here, right? I think that's a good enough separator. I don't know. There we go. That's pretty styling. Okay. You know what I really want though is I actually want that, right? Like duh. Of course that's how it should look. There we go. Separated. Okay, just fooling around for a minute for a little bit of fun. How do I do this efficiently? Well, not efficiently. That's off the table. How do I do this at all? We need to turn this into essentially this. Right? So we're going to end up building a bunch of individual lists, and each of those lists is going to contain everything that the original list contained, and then it's going to contain one of each of these things, and we're going to have to do like a nested loop over each of the things in there, right? And unfortunately that's going to be a little bit non-trivial to figure out how to do, but fortunately it's not going to be too bad, I don't think. We loop over we need a thing that's keeping track of which one we're on for each set, right? So we'll need basically each of those to be an iterator that can go CD and then go CD again. Yeah. Yeah, okay. And then the other thing we get to do is we can watch out for if any of these contradict any of these. So essentially if we, for instance, try to intersect this, and these are non-overlapping, aka this is a bit and this is a bit that are the same flag but with opposite values, so they're opposing pins or conflicting pins, then that part just doesn't even get emitted, right? So those are the things we're looking out for. So first we need to figure out how we're going to do this iteration over, or I could try to first figure out which of these I can mark as not actually possible. It's a hard call, it's a hard call. I think I just want to figure out how to do the iteration first, right? I'm going to do that. Just call it good. I think it's a little bit slower than it needs to be, but it's also the thing that's on my mind the most that I want to get done first. So the hard part about this is there's nothing hard about iterating over these groups. I can go from this to this, right? This is a list, that's a list. I can just iterate those. Within each list I can iterate across them. So I can hit this list and I can go A, B, and then I can hit this list and I can go C, D. What I actually have to do is, for each thing in this list, I have to iterate each thing in this list. So I have to say, give me the first list, thank you. Now give me the first thing in that list, thank you. Now iterate everything in this list, thank you. And there might be more, right? I have to do that an indefinite number of times. That makes me think recurse. So I want to rename this to be smaller. I'm going to just call this pin sub recursive. Or just pin sub actually was what we'll call it. Whoops. And then the result that we're building and then a recursive version. So I need to pass the result pointer around through the system, and I need to take